The next design strategy for natural ventilation is the buoyancy-driven natural ventilation. As we discussed before, the warm air rises because of its decreased density. The sun keeps shining, cooler air with more density move down, and warmer air move up. And a lot of local conventional historical buildings have been utilizing this effect for increased natural ventilation. If you've designed thermal mass that is aided by interstitial spaces, which can be seen in a lot of passively designed buildings, the purpose is to trap the most amount of heat into this thermal mass by the use of this glazing outside. Intention is to release the heat during the night when you need it. The problem for this design is that if you don't have proper control, you will have negative effect during the daytime. It will just keep heating up. This surface will be tremendously hot, and this will work as a continuous radiator. If you have designed this kind of interstitial space for the passive purpose, is crucial for you to design a proper operability, and that operability is usually driven by the buoyancy of the air. During the summer, in order to prevent the problem that I just described of this wall being too hot, you want this space to be continuously ventilating its hot air to the outside. And during the winter, you would like to close this window as much as you can to trap the most amount of heat inside when you need it the most. For this wall, during the summertime, you would like to close it in order to prevent the hot air from coming in to the interior spaces. And during the winter, since you have closed this already and you are now trying to collect the most amount of heat inside, and you want that to be moving back into this interior space through the buoyancy effect. So therefore, you want to open these two opening up during the winter time. So this kind of design not only requires careful design, but also requires a careful operation. Let's discuss how buoyancy-driven ventilation work and how to design in more detail. Let's say you have a building with certain height and a heat source inside of it. And what you are doing by building this building is creating its own environment. Every environment with air has a stratification of pressure. As the elevation goes up, you have a lesser amount of pressure. Let's say this is the pressure. For example, higher up in the mountain have low pressure, and ground surface has the higher pressure, and it moves gradually in a straight line. And by creating this micro environment inside the building, you have now increased the pressure at this elevation certain amount, and since the hot air moved up, you have now lower pressure at this elevation, and it happens in a gradual fashion. And this graph is now nicely showing that effect. And you have outside pressure and inside pressure. If you locate a opening at this location, at this elevation, you have pressure difference by this amount. And if you locate an inlet at this location, you have a pressure difference by this amount. And that pressure difference is what's creating an air movement inward and outward. And in here, there is a neutral plane. This is point where exhaust air and incoming air is divided. If you have any opening that is below the neutral plane, there will be air coming in because indoor air pressure is lower than the outdoor pressure. If you have any opening that is above the neutral plane, you will have air moving out. In terms of its magnitude, because the both pressure stratification happen gradually, is proportional to its geometrical location. As the opening is closer to the neutral plane, you will have less pressure difference. Therefore, you will have less air movement. You will have more air movement as the opening is further away from the neutral plane. It's very important for you to control this neutral plane, and depends on where this neutral plane exists. At some elevation, air will move out, and some location air will move in. You can control the elevation of the neutral plane based on the size of the opening. In this case on the left, since large openings are located towards the bottom and just the small openings are at the top, neutral plane is located more towards the bottom. On the right, since the uppermost opening has the largest size, the neutral plane is shifted upward.